All right. Today we're gonna get improper. I know that's a really dumb joke, but I can't help myself. I'm a mathematician. I make dumb jokes. This is why I'm not a comic, but it makes me laugh. So we're gonna talk about improper integrals today. Before we even do that, I know you read through the book, but I want to talk about the example that they give you in the book. This idea of this function, f of x equals 3 over x squared. And let's consider the area under f of x from 1 to infinity. Okay, so this is kind of an interesting idea now that we haven't considered before. We know how to take area, right, between two x values like 1 and 7. I could do that. I would set up a definite integral. I would evaluate it from 1 to 7 and take the antiderivative and all of that good stuff. But the question now is, well, what does this mean to find the area on an infinite interval? And not even what does this mean, but can we do it, right? That's really the question. I mean, this is kind of crazy talk, right? I'm asking you to find area under this curve over an infinite interval, which really, if you kind of think about that, seems a little silly. How could I have a finite area that is taken over an infinite interval? Okay, so what I'm going to do is I'm going to just graph this. So when x is 1, y is 3. When x is 2, y is 3/4. This guy starts hugging the x-axis. I don't think that's a math term, hugging the x-axis, but and at 1/2 we're all the way up at like 12 or something. So when I graph this, it looks kind of like 1 over x, but because that denominator is x squared, this guy actually, gets a little closer to the x-axis faster than 1 over x would. So my question then is, well, first off, is this area finite, right? Does this guy, now I know that this function right here never actually crosses the x-axis. For it to cross the x-axis, right, that means the function would have to equal 0. What is the only way a fraction equals 0 is if the numerator equals 0, but the numerator is 3, so 3 is not 0. So it never crosses the x-axis. But in mathematics, we've dealt with limits before. I don't know why I feel like coloring this in. We've dealt with limits before, right? And remember what a limit means. A limit means I can get as close to a number as I want by maybe taking x values as close to another number or something like that. So limits are going to be involved with this. And before we actually get to limits, maybe I could just kind of estimate to the area by starting at 1, and then, I could integrate from 1 to 2, I could integrate from 1 to 3, I could integrate from 1 to 5, and I could kind of see, well, is my area kind of approaching a number, right? And I could maybe guess as to then what the area would be. So what I'm going to do, so instead of evaluating, like 10 different integrals, saying I'm going from like 1 to 2, 1 to 3, 1 to 5, 1 to 1,000, 1,000. That's also known as 1,000, 1 to 1,000. Could I figure out how to do this without having to do 10 different antiderivatives, 10 different definite integrals? So what we do is we say, okay, well, let's just pick some point B and let's find the area between 1 and B. Okay. Now this is a little silly, but it'll be okay. I take the antiderivative. Remember, this is 3 to the negative 2. So I add 1 to negative 2. That gives me negative 1, and I divide by it. So I get a negative 3 over x evaluated from 1 to b. If I plug in b, I get 3 over b. If I plug in 1, I get a negative 3, but remember, I'm subtracting that negative, so I get a positive 3. So look at what this is saying. This is saying that the area from 1 to b, depending on whatever b is given by negative 3b plus 3. So if I wanted to estimate the area, right, I could pick different values for b, and I could actually plug that into this guy right here. And I could say, okay, well, what if I wanted to estimate the area from 1 to 2? Okay, if I wanted to estimate the area from 1 to 2, then, and I'm getting my calculator out here because I don't trust myself. If you watched my last video, you should not trust me doing arithmetic. All right, so I'm going to put in 2 for B. I'm going to take a negative 3/2 plus 3. I know what that is. That's positive 3/2, which is 1.5. So I know that the area then between 1 and 2 is 1.5. Well, that's not a very good estimation of the area from 1 to infinity, right? 2 isn't really very close to infinity. Let's get a little bit bigger here. How about 10? So if I have a negative 3/10 plus 3, I can even do that in my head. Very proud of myself. I get negative 2.7. So now I have found, I let B go to 10. I have found, you know, that the area from under the curve from 1 to 10 then is about 2.7. So let's get even better. Again, what do I want? I want this B to go to infinity, right? I want this guy to go to infinity because that's what I'm looking for. Let's put in 100. Oh my goodness, we're getting crazy. Now, I know it's 300ths, but I don't trust myself to do arithmetic. I swear, once I got to graduate school, my arithmetic skills were just horrendous. So I don't always trust myself. I have to grab the calculator. So look at this. This is kind of interesting. Look at what this looks like, what's happening. It looks like my area might be approaching a number. I don't know. Let's get a little crazy. Let's put in 10,000. Okay, so now what is this giving me? This is giving me the area under the curve from 1 to 10,000. This is gonna be fun. I could do this all day. Oh, look at that. So I plug that in and I get 2.9997. And if I plugged in a million, right, I would get 2.9999 something, 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 7. If I plugged in 2 million, I'm just going to get closer and closer to 3. Okay, I'm going to get closer and closer to 3. So what we can actually say then that the area underneath the curve from 1 to infinity of 3 over x squared dx, it actually is going to be 3. This, what I've shown you right here, is not a proof. This is just playing around with the numbers, seeing if we can see a pattern. But the important thing here to realize is if I look at this equation here for area that I got, this negative 3 over b plus 3, the idea here is that b is approaching infinity. And what do you notice would happen with 3 over infinity? Okay, and now I can't actually take 3 over infinity. Infinity isn't a number, so don't treat it like a number. But what I can think about is if I have negative 3 over b plus 3, this guy right here is going to go to 0 as b goes to infinity, okay? Why does that do that? Because I'm taking 3 and I'm dividing it by really, really big numbers, right? If I take 3 and I divide it by a million, that's a very, very small number. So anytime I have a relatively small number divided by a really, really big number, that guy is getting smaller and it's gonna go to 0. Okay, so that's what we mean by limits at infinity. And this is how we're going to evaluate these improper integrals. We're going to basically, we're going to come up here, we're going to replace this infinity right here with a b, and we're going to put a limit as b goes to infinity out front here. Okay, so let's write down some definitions for this. And I actually kind of don't like how your book did this because it didn't quite give you all the definitions you need. But we'll just start off. I just want to give you these 2 definitions that are going to be important for us. All right, so I'm just going to say, let's let, I'm going to say, let's let f of x, okay, be non-negative. We don't always have to have non-negative. I don't know why your book's worried about the non-negative, but we'll just say non-negative for right now. Doesn't have to be non-negative. We can do improper integrals with non-negative numbers. It doesn't, or non-negative functions. That's not a big deal, and we can actually get get the integral to exist even if it's non-negative. But that's okay. If they want non-negative, we'll say it's non-negative. And I'm being a little lax here because I want to do a kind of a good definition here. So, you know, if you're watching this and it's bothering you that I'm not being super, maybe mathematically perfect on this, I'm sorry. I don't know what to tell you. All right, so let's finish this up. So let f of x be non-negative. I don't even really care about that. But there are two definitions here. If, okay, if I'm taking a to infinity of f of x dx, okay, so I'm going from a up to infinity, then we can write, here's the definition. Here's what we're going to do. We are going to replace that infinity with b, okay? And I'm going to evaluate this from a to b of f of x dx, okay? Our definite integral, our fundamental theorem of calculus, which tells us to take the antiderivative of this function and then plug in the bounds, does not know what to do with infinity, people. It doesn't. Infinity is not a number. So this is why we have to replace that infinity with a variable b, and then I'm going to take the limit as b goes to infinity. So what we're going to do is we're going to evaluate this part first and then bring in the limit, actually take the limit at the end. Now I'm going to write the limit the whole time because you know that I'm a little bit anal about notation. So I'm going to write the limit both times to make my super sensitive math teacher feel okay. Another way we can do this, and they don't write this in your book, is I can actually look at, well, what is happening to f from the left-hand side as we approach minus infinity? Then we can do the same thing. Then we write, okay, the limit, and I just replace that minus infinity with a, and I'm going to go from a to b. So same idea here of f of x dx. Okay, now I have a quick note for you here. So first note, if the limits exist, the limits are not always going to exist. We say the integral converges or is convergent. Okay, so there's some new vocabulary for you. Have fun with that. If the limit does not exist, I'm running out of room, so I'm going to be a little lazy. Limit does not exist, DNE does not exist. We say the integral diverges or is divergent. Okay, so we say if the limit exists, if once we take the antiderivative and we let the variable go to infinity and we get a number, we say that's a convergent integral, or we say it converges. If we take the limit as x goes to infinity, or not x, as b or a goes to infinity, and it does not go to a number, right? It just blows up, it gets huge, then we say that it diverges. All right. Oh, you guys are seeing my, I need to turn that off, my email. All right, I'm gonna do some examples. And if you haven't had very much experience with taking limits as they go to infinity, which I don't think we did a lot of it in Business Calc 1. What I want, I'm going to kind of do them, I'm going to do some of these limits as we go through and actually evaluate some of this. So let's do a quick example. Let's actually look at how would I really evaluate this integral right here, which we've already done, but I want to show you how I need you to write this notation-wise and how we do this mathematically instead of just setting up a table, right? So I'm going to take the limit as b goes to infinity, 1, and I'm going to replace that infinity with b, and I'm going to rewrite this because I know I'm going to take the antiderivative of it. So this equals, I need to see all of this. I need you to rewrite that infinity with a b. I need to carry down the limit sign because I have not taken the limit yet. Now what I'm going to work on is I am just going to work on, it's a weird shape. I'm just going to work on that part right there. So again, the antiderivative we know is a negative 3 over x, evaluated from 1 to b. Again, I'm going to write the limit sign. I have not taken the limit yet. So b is going to go to infinity. If I put in b, I get a negative 3 over b, and I'm putting parentheses, plus 3 over 1, right? Okay, so Now I'm ready to take the limit. I've evaluated everything I can with this definite integral. Now I'm ready to take the limit. So what you want to think about again is as b gets really, really big, what is happening to 3 over b? I am taking a relatively small number. 3 is pretty small, right, compared to a million or a billion, and I'm dividing by really, really big numbers. So that guy goes to 0. Now what happens to 3 as b goes to infinity? It doesn't care. 3 don't care. It doesn't. Oh, my English teacher father, I can hear him already mad at me that I just said 3 don't care. 3 has no b in it. So no matter what happens to b, it's just going to be 3. So what do I know about this integral? It converges. And this is a pretty bold statement, right? To say, hey guys, I can find that area underneath that curve. That's a horrible picture, but pretend that area is finite. Not only is it finite, it's 3. I know what it is. It is 3. And again, what this is saying here is that I can get as close to 3 as I want by taking b's that are sufficiently large, right? Maybe I'm at 2.997, but I want to know, okay, I want to get closer. How do I get closer to 3? I want to be at 2.99999999997. I would be able to find a b, right? If I find b big enough, then this guy is going to be small enough to make this really, really close to 3. And the argument is, as b goes to infinity, once I let it go to infinity, remember infinity is not technically a number, let it go to infinity, this whole thing is going to 0. So really, 3, the area under that curve, if I let it go to infinity, is indistinguishable from 3. I hope that makes sense. I know that this could be a little, these integrals can be a little bit confusing. This is why you do the suggested problems that I give you. This is why you do the fun sheet. This is why you email me if you have any questions on this stuff, okay? So let's look at another one. How about the integral from, I don't know. No, let's not do 2. Let's do 0 to infinity of 1 over e to the x. Because I want to talk about e a little bit and kind of see what happens to this. All right, so again, I'm going to rewrite the bound here as b. You don't have to use b. You really can use whatever variable you would like. I don't really care which one you use. Maybe not O. That wouldn't really work out very well. Let's take the antiderivative. Again, I'm writing the limit because I haven't actually taken the limit yet. So b goes to infinity. I would have a negative e to the negative x evaluated from 0 to b. And what is this? This is 1 over e to the x, right? So I plug in my bounds. I get the limit as b approaches infinity of negative 1 over e to the b, right? Minus a negative, if I put in 0, I get e to the 0, which is 1, minus a negative 1, which is plus 1. And again, I have this situation. Let's think about e, right? E is approximately 2.718281828459045. I know you're impressed. I know e to 15 decimal places. I am a hit at parties, let me tell you this. So e is approximately, it's an irrational number, so I can never put equals 2.71828. Sometime if you want to know my trick for remembering that, I'm sure you guys will just be emailing me like crazy. Just email me and let me know. So there's my e. Look at what I'm doing to e. So e to the b, right, is going to go to infinity as b goes to infinity. Because I'm taking e, I'm raising it to like a million. So I'm basically taking a number close to 3, and I'm taking 3 to the million. But then that number right there is going in the denominator. So this guy's getting huge. So what is happening to the entire fraction? It's getting really, really small. If you don't believe me, take 1 and divide it by any really big number in your calculator. Take 1. That's why we say like, oh, he's 1 in a million. Right? Or she's 1 in a million. That means that there are only a few people like that. We don't, it doesn't mean, I don't know how I got on that topic. I'm not going to keep going there. So this guy goes to 0. So what is my limit? It's 1, and it converges. Okay. All right. So let's do another one. I want to do one that involves, whoa, how did that get red? That's too angry of a color. I want to do one that involves some substitution. So how about, let's look at the integral from I just want to make sure things work out here. 2 to infinity of x squared over x cubed plus 1, let's say, dx. Okay, so I'm going to take the limit again as b goes to infinity of the integral from 2 to b, all right, of x squared over x cubed plus 1 dx. Now, of course, you notice that we're going to need to do substitution with this. So I'm going to do a bit of side work over here. Now, you could change your bounds. This would be fine. You could change your bounds, but I found some students kind of get confused when I do that. So let's do some side work, okay? So what do I know? I need to find an antiderivative of this guy. So I'm going to do some side work here because, again, notation-wise, I can't put that this right here is equal to this because I'm not going to change my bounds. So I'm going to let u equal x cubed plus 1. du then is 3x squared dx. So I get 1/3 du equals x squared dx. Okay, so what do I have here then? I have 1/3 times 1 over u du. Okay, and if you can kind of see what the solution is going to be, you're fine just doing that also. So my antiderivative is 1/3 natural log of u. Okay, I'm not going to worry about the plus c because I know I'm going to be plugging this back into here. So remember what the fundamental theorem tells us. I don't know if I ever called it that, but I'm going to call it that. And then I'm going to plug my u back in, right? Oh, I forgot to do that. Oh, how embarrassing. Okay, so I'm going to plug my u back in, so I know the antiderivative is 1/3 natural log of x cubed plus 1. Again, that was my side work to find the antiderivative, just so I didn't have to change my bounds. You could change your bounds. It'll involve a b, but that's not scary. Like, who cares if there's a b involved, right? All right, so here's what we got. Notice how I'm rewriting my limit signs. Yes. Limit as b goes to infinity of 1/3 natural log of b cubed plus 1 minus 1/3, looks like it's the natural log of 9. Now I wanted to do this one because this is kind of an interesting one. We haven't really talked about what happens to natural log. So if I look at this, I have the natural log of b cubed plus 1. What is happening to b cubed plus 1 as b goes to infinity? Well, this guy right here, as b goes to infinity, is also going to infinity. You're cubing infinity, basically. You're cubing really, really big numbers, and you're adding 1 to it. So let's think about what happens. Let's look at the graph of natural log. So everyone remembers the graph of natural log. Graph of natural log does this. So look, as I'm taking the natural log of bigger and bigger numbers, what is happening to the function values? They're getting bigger and bigger also. So I know that this whole thing here then, as b goes to infinity, this whole thing is also going to infinity. It must. I'm just taking bigger and bigger numbers, bigger and bigger x values, and look at this function is just getting bigger and bigger. Then we're going to take 1/3 of infinity, which let me tell you, it's still infinity, and we're going to subtract this tiny little number. Infinity doesn't care about 1/3 of natural log of 9. It's still going to go to infinity. So what's happening here then is this guy is going to equal infinity, and we say that this diverges. Okay, what that means is, that means that the area underneath the graph of x squared over x cubed plus 1 from 2 to infinity goes to infinity. Okay, it doesn't approach a number. It doesn't get close enough to the x-axis fast enough for that area to be finite. I hope that makes sense. A couple things really quick about limits. Some useful limits. I don't know why I'm stuck with my green. So I just want to write down some useful limits that you might need, okay, as you work your homework. So the limit, we kind of saw this one already. Now you'll have b's or a's or whatever in here, but we saw e to the negative x. This guy goes to 0, right? Because that e to the negative x, that's 1 over e to the x. The limit of just e to the x is going to be infinity. You're taking basically e raised to, and if you look at the graph of e, here's the graph of e. Whoosh. You have to make that sound when you graph e. You have to make the whoosh sound. That's the graph of e. So obviously as x goes to infinity, e to the x is going to get really, really big. Another useful one, the limit as x goes to minus infinity. So minus infinity is going to be going this way. What is the limit of e to the x as I go to minus infinity? That guy's actually going to be 0. Think about that. That makes sense, right? As x goes to minus infinity, I'm taking negative values, so I'm raising e to a negative value, which in turn is going to throw that guy in the denominator. Okay, so I'm going to get like basically 1 over e. Likewise, if I have the limit as x goes to minus infinity of e to the negative x, when I plug in that negative infinity, the negatives are going to cancel. I'm not plugging in negative infinity, I'm plugging in big negative numbers. So those of you out there, don't leave me comments that I know I can't plug in negative infinity. But as x gets really, really large negatively, the negatives cancel. So these are some important limits that involve e. Another important limit as x goes to infinity, natural log of x, that guy's going to go to infinity. Again, because the graph of natural log of x, which is just the reflection of e, right? That guy's going to infinity. Now, anytime you have an x on the bottom, that guy's going to go to 0. So if I have something like this, x goes to infinity, 1 over x to the, let's say, k, where k is any number bigger than 0. Okay, any number bigger than 0. So k needs to be greater than 0. This guy is going to go to 0 because my denominator is going to grow so fast that it's going to go to 0. If that x is on the top, it's not going to 0, people. It's not going to 0. So for example, I just want to do one more. Oh, we're almost at 30 minutes. But these are just so fun. I just really like doing these. I want to find you one that diverges from the minus infinity side. Oh, I don't see one that's going to be easy enough to do. Actually, we could do this. Let's try this. Minus infinity to maybe -1. 1 over the cube root of x dx. Okay, so let's quickly see what happens here. So I'm going to take the limit. I'm going to replace that minus infinity with like a, or you could use b. I don't care. Seriously, you could use b. A to -1, x to the -1/3 dx. Okay, so I get the limit. I hope you're still with me. I know when we get close to 30 minutes, I've probably lost a lot of you. I'm going to add 1. That'll give me 2/3. Divide by 2/3. That gives me 3/2. I'm going to evaluate from a to -1, which I know that's weird that I have the -1 in first. But look at what this is asking here. If I look at the graph of 1 over cube root of x, which I'm not exactly sure what that looks like. I could plug in some numbers. At -1, I'm at -1. I don't know. At -8, I'm at like a -1/2. And so I think it's gonna, I don't know what actually it looks like. I can't put in x equals 0, right? Maybe. I think I've ever, and when I put in 1, I get 1. When I put in 8, I get 1/2. So I think maybe something like that. Anyway, so if I look at this, what I want to show you, my point in all of this, and I'm sure you're asking that, Sarah, what is your point? I have one. I have one. My husband doesn't always think I have one, but I do. So if I put in -1, okay, take -1 and raise it to the 2/3 in your calculator. What this is asking you to do is it's asking you to square -1, which is 1, and then take the cube root of it, which is 1. So I get 3/2 minus 3/2 a to the 2/3. Now I know this looks like it's maybe going to converge, right? I'm looking for this area right here. It actually doesn't. So if you look at this a to the 2/3, here's what you're doing. You're basically taking a and squaring it and then taking 1/3 of it, right? That's what the 2/3 means. So what's happening to a squared as a goes to minus infinity? So I'm taking like a -1,000,000 and I'm squaring it. This guy, my friends, it's going to infinity. And then if I cube root infinity, well, that's nice. That's cute to try and cube root infinity. You're cube rooting really, really big numbers. They're still getting really, really, really big. So what's happening here is this guy actually is going to infinity. A negative infinity, right? Because of this minus sign in front, but it's still going to infinity. So I would put a minus infinity as my answer, just because it's going to be negative here. And we say that this diverges. So anytime I get, you know, if that guy had stayed in the denominator, which it didn't, but if this had been my answer, right, 1 over a to the 2/3, that guy would go to 0. But a to the 2/3, as a gets really, really big, that guy's going to infinity. I hope that makes sense. I know these infinite limits can be kind of tough. Hi, I'm 6 seconds over 30 minutes, so I'm going to stop talking. Holler at me if you have any questions.